Yes, sir.
Yeah, so what do you ask about the bulb? If you buy a bulb, what do you ask? Right?
Voltage.
Voltage. No, no. So you don't ask about, you ask that what's the wattage? How much watt is this bulb? Right? This is you ask.
Yeah. Yes,
Yeah.
sir. I
So
got
what?
confused.
Yeah, yeah, yeah. So you ask about the power. What is the power is denoted by what? Right? So you ask about the power. So whichever bulb has more power, then it will glow brighter. Right? So that is the idea of the equation. So you generally get 100-watt bulb, but now you have LED bulbs, so they are 7 watt, 5 watts, and 12 watts, and it's kind of. So you always ask about the power of the bulb. So how much wattage is of that bulb, right? So in this and we have already calculated the power of resistance or any device, right? So what is the power? How do we calculate the power? Do you guys remember how do we calculate the power? Yes. How do we calculate the power, guys? So V into I or I square R or V square by R. This is how you calculate the power, right? Remember now.
Yes, sir.
Okay. So now we have two different situations. In one situation, let's say some voltage is applied. Like let's say this is okay. Let me write as and I have so bulb is denoted by this notation. Okay, this is how the bulb is my diagram or my let me properly. Okay, so this is how you denote the bulb. And this is how you denote the resistance. This is how you denote the capacitance. And this is the symbol of what? This symbol is of what? Yes. So in your lab, in your Viva, your practical exams, they may ask you these kind of questions. So what is this? Yeah, if we write something like this, so what does this denote? Sorry guys, I'm asking too many questions. Yeah, so only for the practical purpose. Yes, any of you guys remember what is this notation? Okay, if you remember this notation, what is this notation?
Rheostat.
Rheostat, right? Rheostat meaning variable resistance. So in rheostat, you can vary the resistance, right? Good, good. So this is rheostat, and this is the notation for variable capacity. Okay. So these are the different notations. So I just yeah, take that. So we have this, and some current is and yeah. So we have two kinds of situation. In first situation, there are three bulbs like this. Okay, so this is one combination, and this resistance is R1, R2, R3, right? Or let me just write out the numbers. So let's say this is 3 ohm, this is 4 ohm, and this is 5 resistance. Okay. Now we have another situation, and in this situation we have these three bulbs. This is 3 ohm, this is 4 ohm, this is 5 ohm, and this is B, and this is 5. Okay. So this is a parallel combination, right, guys? And this is a series combination, right? So whenever they ask about the glowing of bulb, what should we calculate? Yes, what should we calculate, guys? So I gave the example of market, and Maria gave the right answer. So what do we calculate?
What?
Power, right? What? Power. So we calculate power. Yes, correct. So we calculate power. So in these two situations, we have to calculate power, and whichever has the higher power, so that would glow bright, right? So we have first case. This is parallel case, and this one is the second case, which is. So now Maria Aisha is not replying, so let us direct the question to her. So Aisha, what is same? What is same in parallel combination? What is same? What remains the same? Yes, Aisha. What remains the same, Aisha, in parallel combination? Yes, Aisha. V is constant in parallel. Yes, absolutely right. V is constant. Yeah. Yeah, both of you guys are correct. So V is constant. Oh, yeah. I is constant. Oh, so you. Okay, Aisha. Yeah, yeah. So you already gave the answer of the next question. Yes, I value. Yeah. Okay. Yeah, yeah. So both of you guys are correct. You guys are revising. Good, good, good. So let me write the number so that it becomes clear. So let us write this as 6 volt, and let's write this as 3 ampere. Again, this is 6 volt, and this is 3 ampere. Right. So you see that in parallel case, we remain, both of you guys say, we remain same, right? And remember that we have to calculate the power. So power has how many definitions? Power is VI. Power is I square R, and power is V square by R. So in parallel case, which remains the same in parallel case, right? Which remains the same? You guys have already told the answer. So voltage remains the same. So which formula we will use? This one or this one? To compare the results, which formula we should use? This is a more general formula, so we will not use it. Between these two, which formula we will use to compare the results?
The second one.
This one,
I
right?
square R.
No, 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 no. So V is same, right? So voltage is same, voltage is same, voltage is same. So then we can compare the results, right? Because one thing is same, right? Then we can talk about these resistance, right? I is changing. So here I is different, here I is different, here I is different. So we cannot talk about the power, right? But in this case, so same voltage is here, same voltage is here, same voltage is here, right? So we can talk about different powers. Did you guys understand that? Yeah. Did you guys understand?
Yes, sir.
Right. So I know that the voltage is 6 here, 6 here, 6 here. Right. So let us calculate. This is bulb 1, this is bulb 2, right, and this is bulb 3. Okay. So in bulb 1, the power is, let's say, power is V square by R. So this is 12 watt. And bulb 2 has power 6 into 6 by 4. So this has 2, 3, and this is 3. So 9 watt. And power 3. So you see that this is 6 into 6 by 5. So 36 by 5, so 7.2 watt. Right. So now let's say if I have chosen this formula I square R. So for this case, this would have been I1 square R, this would have been I2 square R, and I3 square by R. But I don't know I1, I2, I3, right? So that is why I chose this formula. Any doubt in this, guy?
No, sir.
So, so you guys can clearly tell me now that we can see that power 1 is greater than power 2, which is greater than power 3. So this will glow brighter, right? So number 1 bulb glow brighter than second and then third. Any doubt?
No, sir.
Yeah. So you guys saw that in parallel case, whoever has the least amount of resistance, so that bulb will glow brighter. Understood? So in a parallel case, whichever bulb has least voltage resistance, that will glow bright. Okay. Now you guys first note it down and then tell me about this. So you guys note it down and then tell me about. This is bulb problem. Okay, so you guys note it down and then whenever you want me to scroll down the page, you guys
Sir, can you please scroll down?
Done, guys.
Yes, sir.
Aisha, noted. Okay, so you guys tell me about what is the power. Okay, so what is the power for first one, and so what are the powers? What is the one? Yes, so which formula you guys will use?
I square R.
Yes, yes, correct, correct. Yeah, so current, right. So we calculate I square into 1. Calculate 27 or 36, 41. So 27, this is Mariam answer, 36 and 41. 27, 36, 45. Yeah, so Aisha also got 27, 36, 45. If both of you guys are getting same answer, so yeah, so you can see that power 3 is greater than power 2 greater than power 1. So you can tell that third bulb will grow brighter than the second one will be first. So you guys can see that the combination is very important in case of the bulb, right? So if we want to higher resistance bulb to glow brighter, so we will connect them in series. Or if we want to glow the lower resistance one brighter, so then we will connect them in parallel. This is the idea, right? So in series case, whichever bulb has most or highest resistance that will then do right. Okay, so you guys quickly note it down and then start. Then we'll start the next chapter. But I am only talking about parallel case only and series case only. Whenever you have mixed cases, so you will see that some bulbs are connected in series, some are parallel. Then what you will do? What you will do, guys? Yeah. What you guys yes, use VI. No, whenever mixed bulbs are given, then the idea is what? Idea is to check the power, right? So we will calculate as like the resistance case, right? So this is a mixed problem. So what we will do is that we will calculate the individual powers, right? And see which one is higher. So let's say I change this resistance to some bulb, right? So you guys calculate the individual powers and then check who has the highest. Understood?
Yes, sir.
Okay. So you guys have noted it down. So now let us move on to the next slide. So magnetic and the first one that we do is bio. uh, Okay, so the next chapter is about magnetic effects of current, right? So in the very early eras, in let's say 1700 and before 1600, so the magnetism was already discovered, right? So people had discovered the magnets, and so the magnets have some regions around them in which they can influence the other magnetic field, right? So the electricity or the electric field, the charge property of the electric field was discovered. Simultaneously, the magnetic property was also discovered, right? So just like you have electric fields, you have also the magnetic field, and these magnetic fields arises due to the movement of the charge. So let me, yeah. Okay, so Orsted was the scientist who discovered that if the charges are moving, so they will have some current, and he, by his experiment, proved that those current will have some magnetic fields, right? Those current will have some magnetic because he created some current carrying loop, and beside that he placed some magnet, right? A magnetic compass or magnetic needle. So whenever he placed that needle at adjacent to the current loop. So he found out that the compass or the needle, right? The needle got deflected. So how can the needle got deflected? If the current carrying loop are carrying some magnetic property, then only that that needle can, right? Otherwise, it will not move. So this proves that the current carrying charges have the magnetic, right? So let us talk about the magnetic, right? So this chapter will be very analogous to first chapter. Whatever we have learned in the first chapter, so the topics would be very much similar to the first chapter. So just like a charge has electric fields, so current will have magnetic fields, right? So in there you had what law? So if there are two charges, so what is the law that defines the force between those two charges, right? So what is the law? Yeah, Coulomb's law, right? So Coulomb's law states that whenever we have two charges, so the force will be proportional to something, right? So this we learn. Similarly, there is a Biot 7. So this relates the magnetic field with the current and the distance between the point that we want to calculate. So first, let us talk about this magnetic field. So area or region around the magnets, right, or current carrying wire, where the force or the effects of, where the effects of the magnetic material can be felt or experienced. Right. So the area or the region around the current carrying wire or the magnets or the magnetic materials where we can experience the magnetic effects. Right. So that will be called the magnetic. And what can you say about the nature of this magnetic field? Will it be scalar quantity or the vector quantity? Yeah. Will it be scalar quantity or vector quantity? I'm just talking about that. We can take the analogy from the first chapter. So magnetic field is analogous to electric field, right? So what can we say about the nature of this magnetic field? Will it be vector quantity or scalar quantity? What is electric field? Is it a scalar quantity or a vector quantity? Yes. Okay.
Scalar.
Electric field is a scalar quantity. E. This is F by Q, right? F is QE, right? And E is F by Q. So force is vector quantity, so electric field is also a vector quantity. Yes, Aisha. So you are correct. So this is a vector quantity, right? and it is denoted, or the SI unit is Tesla, right, which is denoted by T. And CDS, in CDS system, unit is in CDS system, the unit is Gauss. So this is more general. So in everywhere you will see that the magnetic field is represented by this. Okay, and this Tesla is related with this Gauss by this much. So this is, and if this is a vector quantity, so it follows vector sum. Okay, right. So you guys, please note it down, and then we'll talk about the magnetic field strength, magnetic field intensity, or magnetic field density. All these three terms are there, and yeah. Whenever you guys have noted it down, please tell. This is chapter.
Done, sir.
Yeah. Okay, so what can be the cause of the magnetic fields? Right. What can be the cause of magnetic fields? So it can be produced by current carrying wires. Okay. And the other would be some magnet. Right. So, and the other one is the intrinsic property, which is the spin, which is a quantum effect, but we will not talk about that. So these can be the cause of the magnetic fields, right? And the next topic is magnetic field strength, or we can call it magnetic field intensity, or we can call it magnetic field density, right? So magnetic field is not a measurable quantity. We cannot measure magnetic field, but we can measure the magnetic field strength, right? Because magnetic field is defined everywhere in the space, right? but we can only measure the some patches of space, right? So whenever we measure the magnetic field in some patches of space, so that is called the magnetic field strength, right? And this is denoted by, okay. So whenever we write V, so this means magnetic field strength, not the magnetic, right? But people unconsciously or unknowingly call it magnetic field. But this is generally magnetic field strength. Is that clear, right?
Yes.
Okay. So how can we calculate this? And I will call it magnetic field, right? So strength, you whenever I call it magnetic field, you guys just understand that I'm talking about magnetic field strength. Okay. So how can we calculate the magnetic field of a current carrying wire? Right. So magnetic field of current carrying wire. Before I do that, so do you guys remember that what is this direction and what is this direction? Yeah. So we have talked extensively about the rotation. So what is dot and what is dot and what is cross?
Dot is cos theta and sin is sorry, cross is sin theta.
No, no, no. No, I'm not talking about the vector products, dot product or the cross product. I am talking about these rotations. So whenever I write dot in electric field, we understood about these rotations, right? When we were talking about electric dipoles and other things, then we came across these two rotations. Aisha, can you recall what are these two rotations? In vector representations, what are these two rotations? Okay, Mariam and Aisha, you guys have forgotten. So this is outward direction and this is inward direction, right? Because let's say this is an arrow and when you see the arrow coming at you, so it is coming out of the whatever screen or whatever. So when you see arrow coming at you, so you will see the point of the arrow, right? So you will see the point of the arrow. And when you see that the arrow is moving away from you, so inward, so then you will see the tail of the arrow. Tail is in this shape, right? Head is in this shape. So that is how you decide the inward and outward direction. Is that clear? Yeah, is this
Yes.
and we can also represent the inward direction or outward direction in I, J, K notation. So if I write K hat, right, this is inward or outward? Yes,
Outward.
outward, right? K hat is coming out of this. So this is X, this is Y, and then this is Z. And minus K hat is inward, right? Okay, so we know about direction. So magnetic field of current carrying wire is it is given by 5 volts, 7 volts, right? So what does the Biot-Savart's law say? So let's say that we have a current carrying wire, right? And the current is, let's say, I. And let's say we take a small element here, small length element here, right? This is a vector. And we are measuring the magnetic field at this point, right? So this is R, this is position vector, or whatever you call displacement vector, right? And this is the angle between the length element, right? And the displacement vector or distance, displacement vector between this point and this point. So is this diagram clear to you guys? Yeah, is this diagram clear?
Sir, can you explain again?
Yeah, so we have a current carrying wire, right? We have a current carrying wire and the current is flowing in this direction, right? So what we do is that we take a very small, so let's say this is a wire, right? And we take a very small portion, ds, length, and we are calculating the electric field, let's say at this point, right? So this is current carrying wire. We take a very small element, very small length element, and then we are calculating the magnetic field due to this current at some distance, right? So is the diagram clear to you guys?
Yes, sir.
Yeah, so this is given by Biot-Savart's law, and it says that the magnetic field will be, so let me write all the instruction that, so we are calculating the magnetic field, magnetic field at B, where theta is the angle between the distance or displacement and the whatever it is, the length element dl, right? Dl, and this is displacement, which is r. Okay, so this is this, and then Biot-Savart's law says that this magnetic field will be directly proportional to current, right? And this will be directly proportional to sine theta, right? And this will be directly proportional to TL. Oh, and this will be also directly or inversely proportional to 1 per hour. Okay, so I am only talking about the magnitudes, right? So when I combine these quantities, so I will I remove the proportionality constant, so I will get mu naught by 4 pi and I dl sine theta divided by r square. This is clear to you guys. So this is the proportionality constant. Okay. So you guys compare with the charge. So we calculated the electric field as 1 by 4 pi epsilon naught, and this is what? Let's say q by r square. Right? That is how the electric field varies. Am I correct, guys? Yes. Am I correct? So you see that I am getting 1 by 4 pi epsilon naught. So epsilon naught is the proportionality constant, and in here mu naught is the proportionality constant. right? Mu naught by 4 pi. So this is very analogous to the electric field. Is that clear to you guys? Yeah. Is this clear?
Yes, sir.
So if I want to write it, so this is the scalar form of the Parseval's law. This is scalar form, right? I'm only talking about the magnitude. But what will be the Biot-Savart's law in the vector form? So can you tell me what is dl sine theta? Yeah. How do you get something like sine theta? So let's say I am getting something AB sine theta. Okay. So what does this mean? If I am getting AB sine theta, what does this mean? Yes, guys, what does this mean? This is A cross B. Am I correct?
Yes, sir.
So you see, I have only one vector dl. There should be another vector. So can this be I? Is I a vector? Is
Yes, sir.
current is a vector quantity? Yeah. Is current a vector quantity? Yes. Aisha and Mariam, is current a vector quantity?
No, sir.
Right? It is not a vector quantity. So we need another vector to represent the cross product. So if I write something like this, so magnitude of something like this, or yeah, and then sine theta. So what is the magnitude of a unit vector? Yeah, what is the magnitude of a unit vector? Okay, let me just change the question a little bit. So what is the magnitude of this vector, or let me say this vector, or let me say this vector? What is the magnitude of these vectors? What is the magnitude of I hat? Yes, I hat cos. What is the magnitude of a unit vector? What do you understand by a unit vector? So you guys have forgotten the vector classes. A vector has two parts. One is the magnitude and the other one is the direction. So one is the magnitude and the hat part. So let's say that you have a vector. So this is represented by the magnitude and direction. So this hat represents the direction only. This is the unit vector, which means that magnitude is 1. As the name suggests, unit means 1. So all the magnitudes of all these unit vectors are 1, right? So when we calculated I dot I, we calculated I magnitude and cos of 0. So this was 1, this was 1, and this was 1. So then we got 1, right? So magnitude of unit vector is 1. Is that clear, guide? Clear?
Yes, sir.
I can write it like this, and then I can write DL cross R hat. So DL cross R hat will be DL into sine theta. Why? Because magnitude of R would be 1. So I can write dB vector as mu naught by 4 pi I ds cross R hat and then R square. Okay. So you guys tell me if I'm writing it correctly or not. I can write this as I ds R vector divided by R. Did you guys understand this part? Did you guys understand this part? Yes. Is this part clear to you guys? Is this part clear to you guys? Okay. So how I can write DL cross R hat to DL cross R vector? Let me just give you guys a hint that R vector is R and R hat. So I can write R hat as R divided by R. So I can put in place of R hat as R vector divided by R. So R vector and there was R square and then this R, so R cube. So this is called the vector form of Biot-Savart's law. You guys please note it down, and if you guys have any doubt, please ask. So you guys please. And whenever you guys need me to scroll down the screen, guys, and please don't hesitate to ask any question, right? If something is not clear to you guys, please don't hesitate. So don't bother about that I have to repeat or that. So please don't bother about that. And whenever you guys have any question, please ask. Should I scroll down the screen?
Yes, sir.
And whenever you guys have completed noting it down, please tell.
Done, sir.
Then, Aisha, what about you? Yes, what about you, Aisha? Go ahead. Okay, so we have a magnetic field, right? So the magnetic field is mu naught by 4 pi and I ds sine theta divided by r. Right. So here this mu naught, or let me write this mu naught. So this mu naught is called the permeability of free space. Right. In electric charges, what did we had for electric field? For electric field, what did we had? So for electric field, what did we had? Permittivity of it. Right. So free space meaning what? What do I mean by free space? Yeah, what do I mean by free space? Yes, Aisha and Mari. So free space can be air or vacuum, right? Is that
Yes,
clear?
sir.
Yeah. So you see that what does these permeability or permittivity of free space tell? It tells us that the magnetic field and the electric field are dependent upon the mediums, right? So whenever we change the medium, then the electric field and magnetic field change. Understood, guys? So
Yes, sir.
if we place the charges in some medium, then the electric field will change, and if we place the magnetic current carrying wire in some medium, then magnetic field will change, right? So this permeability of free space is telling that it is telling that magnetic field is dependent on the medium, right? So this is what it is. And there is a very interesting relation between the mu naught and epsilon naught. So let's say that the value of mu naught by 4 pi is 10 to the power minus, right? So mu naught by 4 pi is 10 to the power minus 7. And can you guys tell me what is the value of 1 by 4 pi epsilon naught? How much is this? How much is
Okay.
this? K. And what is the value of K? 9 into 10 to the power 9. Yes, correct, correct. 9 into 10 to the power. So we know that what is 1 by 4 epsilon naught. We know what is mu naught by 4 pi. So let me calculate one quantity. What is mu naught into epsilon? Right. So let's say that I divide this mu naught by 4 pi, and then I multiply this by 4 pi. So mu naught by 4 pi is 10 to the power minus 7, and 1 by 4 pi epsilon naught is 9 into 10 to the power 9. So this would be 1 by 9 into 10 to the power 9. Is that correct? So this would be 1 by 9 into 10 to the power 60. So this is 1 by 3 into 10 to the power 8 square. So can you guys recall what is this quantity? Can you guys recall what is this quantity? Yeah. Can you guys recall? Can you guys remember what is 3 into 10 to the power 8? Let me write, so 3 into 10 to the power 8 meter per second. What is this?
Speed of light.
Speed of light. Absolutely correct. So you guys see that mu naught epsilon naught is 1 by c square. So this is the property of mu naught is the property of what? Mu naught is the property of what? We are in what chapter? We are talking about. So we are on which topic? How did this mu naught came? Let me ask this other question. So what is this epsilon naught related to? Yes. What is this epsilon naught related to?
Permeability of free space.
Permittivity of free space, right? Permittivity of free space when we calculate the electric field, right? So this epsilon naught relates with the electric field, which means electric nature. And this mu naught relates with magnetic field, right? So
Yes.
epsilon naught mu naught, which means that electromagnetic behavior. Electromagnetic behavior. And C square is what? C square is what? Light. So that is how we can say that the light shows the electromagnetic behavior, right? That is how we can explain that light is electromagnetic waves. Is that accurate? So we will understand about this electromagnetic waves in more detail when we will do the last EM waves. So in that chapter we will talk about this more in detail. But you guys can see the beauty of these two constant, right? So these constant together can tell us about the light, right? Okay, so I wanted to talk about this only, you guys. Okay, yeah, please note it down. And if you have any questions, so you can ask.
No, sir, no question.
Okay. One time, one moment, please.
and
Yes, guys, noted. Hello, hello, hello. Yeah. So, yeah, noted. Okay, so now we will talk about the direction of, right, because magnetic field is what kind of quantity? Magnetic field is what kind of quantity? It's a vector quantity, right? So when we talk about the magnitude part, we have talked about, right? We have talked about magnetic part in more detail, right? So this is the magnitude. Now let us talk about that. What is the direction of the magnetic? So direction of magnetic. So there are two methods, right? There are two methods to know about the direction of the magnetic field. So first method is right hand thumb, right? So we have a wire, okay? We have a wire and the current is flowing in this direction, right? So we have a wire and the current is flowing in this direction. So what does this is Maxwell right hand, right? So Maxwell right hand. So we have a wire and the current is flowing in this direction. So what does Maxwell says? We place our thumb in the direction of the current, right? And then we curve our fingers. The remaining fingers we curve, right? So you see that this curve is pointing out in this direction. So it is pointing out in this direction, right? So in here it is going in this way, and in here it is in this. Is this a point clear to you? So in here, what do you see? So we have this current and we have curved our finger, right? So in here, it is coming out. And in here it is what? It is what? In here. This palm of our hand is going what? Inwards, right? So in this part, we write this direction, and in this part, we write this direction. So is this clear to you guys? Right. So the diagram was this, right? The diagram was the current was flowing in this way, and we were calculating the magnetic field at this point. So this will be cross, right? So in here and then this would be cross. So in here the magnetic field is inwards. Okay. So in here the magnetic field is inwards. This is the first method. This is DL, and this is R. Is that clear to you guys? The first method? Okay. Now, the second method is about the gross product method, right? So we know that our magnetic field is this is let's let's say that this is TL, right? This is TL. We are calculating the magnetic field in here, and this is the theta, this is the R, right? So magnetic field is mu naught by 4 pi I dl cross R divided by R square. So you know that this is dl and this is R. So whenever we take the cross product of L and R, so let's say that this is C and we take the cross product A. So what can you say about the angles between A and C and B and C? What can you say about the angles? Yeah. So what can you say about the angles? Let's see if you guys remember the vector part of what. So let's say that let's say that I have these three vectors, right? These three vectors. So this is I, this is J, and this is K. Right? This is I, this is J, and this one is K. So if I take the cross product of I with J, so what do I get? Cross product of I and J, what do I get? Yeah, what do I get? What did you say? Cross product of I and J. So I place my palm in the direction of I, and then I take the cross product, and then yes, what is K? Right, K hat. So we know that dl cross K or I cross J will give me K hat. So what is the angle between I and K? What is the angle between I and K? What is the angle between I and K? 90. And what is the angle between J and K? What is the angle between J and K? Yes, angle between J and K?
No, no. 90 degree.
90-degree again. So you see that whenever we take the cross product, so all these, right, so whatever these two vectors are, they will be always perpendicular to this cross product. Understood? So, Rifa has already joined. So you understood that this A vector will be perpendicular to C, this B vector will be perpendicular to C, right? So similarly, DL and R are perpendicular to B. Is this clear? Is this part clear? Is this part clear? Yeah. So I have this one, right? I have this R and I have this DL. Now I want to calculate the direction of DL cross R. So I put my palm in the direction of R, not R, but DL, right? So this is my DL, right? So I put my palm in the direction of DL. and then I move to the direction of R. Right. So I move to the direction of R. So what is this thumb points out? What is the direction that this thumb points out? Yes. I place my palm in the direction of this DL, and my I move to this R. So what is this thumb pointing out? What is the direction?
What?
Inward, right? Inward, right? Inward. Is that clear to you guys? Is this clear?
Sir?
Yes, yes, Maria.
Sir, you were not audible for 1 second.
I was not audible. Yeah. So I told you guys that I want to calculate the direction of the magnetic. Rifa, please wait a moment. Okay, please wait for some. Yes. So I want to calculate the direction of the magnetic field, and that is the cross product of dl and r vector. So this is my dl vector, right? This is my r vector, right? So how do I calculate the direction of the cross product? So this is A vector, this is B vector, and this is the theta. So I place my palm in the direction of A vector, and then I move to B vector. So whatever the direction this thumb points out, so that is the direction of the cross product, right? Is that clear? This we learned in the vector class, cross product. Clear, Mariam? You are not audible. Maybe your internet is not working properly. So similarly, I want to calculate the direction of magnetic field with dl cross r vector. So this is my dl. So I put my palm in the direction of dl, and then I move to r. Right. So this thumb is pointing out inwards. So that is how I can say that the magnetic field is inwards. Understood, Maria?
Yes, sir.
Okay, so I will talk about this more in the next class, and you guys please join the waiting room. So let me make a waiting room, and then please take the class assessment test. So let me, yeah, you guys log into your Learnivio account, and then let me make the waiting. Okay, yes, Rifa, Assalamu alaikum. Sorry to make you wait, but
Yeah, Walaikum assalam. Sir, I joined a little bit early because I have a event like a family
oh yeah,
function.
family
So
gathering.
yeah, no, like
Yes.
a wedding ceremony. So
Oh,
so is it fine if you can end the class a little fast? Because like after after this class, I don't think I will join the next two classes because like
oh,
yeah, I
so
will be out. It's at
yeah,
eight
yeah.
o'clock.
Yeah, you have
It's
told me
local
that,
distance.
you have told me that the duration of this wedding is 14 days, I guess. 14 or 16 days.
No,
Yeah.
no, no. 1 week
1 week.
only.
Oh, 1 week, 1 week. Yeah, yeah, yeah. So please enjoy that
Only
wedding,
till
right?
this Saturday. That's it.
Yeah, yeah. Please enjoy that wedding and have lots of food, right?
Yeah,
So,
okay.
yeah. And let me, okay. So, yes, I have talked, yeah, Aisha and Mariam, I have talked to the Learnivio team, and they will create the waiting room. You guys, did you guys find the active test? Yes, Aisha and Mariam, did you guys find the active test?